Non, moi j'ai appris simplifié. J'ai appris simplifié en attendant 6 ou 8 et je fais de la même manière comme ça. Je suis jamais.
Okay, good morning. So how is a holiday for you guys? Have you been there anywhere? No? Okay, I think we can continue for the last introduction of the vibrating wire transducer. So we will continue this part, and if you have any problem, please raise your hand anytime. Okay. So I think in the last time I showed that the vibration wire transducer right now it is a very very famous part of the transducer or laser sensor because for the previous one I think we just talking about the resistance, the concept of the resistance, and using a strain gauge to detect maybe the force, displacement, or pressure. Okay, and in terms of the change of the resistance, right? However, if just I say in the last time, we just take the voltage change, right? This is the voltage change. Can you see that? Okay, and we can have maybe some strain. Okay, so this is the basic idea of the strain gauge we used so far. But however, if we use a very long distance of the transmission line, okay, so the voltage, I mean the amplitude of the voltage may be decreased with because of the long distance cable. So maybe due to the long distance of the cable, the voltage may be decreased. Okay, so that we may get around a strain. And otherwise, for the very long cable for the transmission, in the last time we are talking about the signal to noise ratio. Ratio. So that's why we call the SNR. So with that condition of the very long transmission line, so the signal to the noise ratio will be decreased. So sometimes maybe we have the signal like this one, okay, with the time, but somehow the noise increase, right? So that's why we may get a very bad quality of the signal if you use the strain gauge to measure during with a very long transmission line. So to reduce this condition, so that's why we develop a vibrating fixed wire. Okay, this is the fixed wire. So this wire have its own natural vibrating frequency. However, if the length of this wire change, means that the natural vibrating frequency will change either. Okay. So the frequency change means that the signal from the vibrating wire originally it will be like this one. Oops. So I just count, maybe in the 1 minute, how many steps we can have. So this is 1, 2, 3, 4, maybe 4 steps. Means that this is the original frequency we can get. And it is very easy. I mean, you don't need to quantify the absolute value of this voltage. For example, maybe this is a 5 DC. But I can easily count 1, 2, 3, 4. I don't need to check, oh, maybe this is the 5.01, and this is the 5.1, 5.02. I don't need that. Just a very simple idea to count the step. Also, it is maybe reduced by the very long transmission line for this kind. Maybe we change to this. If I have a very long transmission line and a very large attenuation, of course, but however, I can still count the step very easily, right? So this is the very simple idea that we change to measure the absolute voltage value in terms to the count the number of the step, so that we can prevent the problem of the very low signal to noise ratio with the very long transmission line. Okay, so that's why right now so many sensor and transducer change to the vibrating wire transducer. Okay, so based on this, right now maybe in a geotech or in the hydrological application, mostly maybe we can find that this is the piezometer for the water pressure. Okay, and this is the extensometer to measure the displacement. Okay, and I think this is maybe the same. And this is the liquid level. Okay, and this is the earth pressure. So based on the strain gauge, we can change the core of the strain gauge and change with the vibrating wire transducer. Okay, with this one, and we can get the advantage. Just as I said, we can just count the step of the signal without any quantification of the voltage. Okay, so I can easily check the displacement or the strain or the pressure. Okay, so this is the strain, the vibrating wire transducer we used so far, and I think this is the mostly, if you type the vibrating wire transducer, you can get so many. Okay, let me close it. So we can get a very easily measurement and a very good quality of the signal using a vibrating wire transducer so far. Okay. So I think in this chapter, I will very quickly show the most principle of the transducer based on the different kind of the physical principle. So right now, I just show you the electrical instrument. So the next I would like to introduce a very simple switch, not a game switch. Do you have the switch? So far, it is hard to find and hard to buy in the Taiwan because the disease. Everyone stay at home and buy the switch. Okay. I tried to buy a exercise with the ring. Do you know that? But the store said maybe after the May or June they have the stock. No, right now this sold out. Okay, so this is based on the magnet switch. So I think this is a very simple idea. If you use a magnet, and so this line will be open or be shorted. Okay. So sometimes we can use this switch and with the external magnet, so we can open the signal and maybe have to conduct the signal. Okay, so it's a very simple idea at all. And this one is every time it is very hard to say. Magnetostrictive, very long word. But I just want to say that it is another magnetic field. So it's just sending a pulse. Okay, so if you send in a pulse with a magnet here, so then I will have a reflection of signal. So this is also a very simple idea. I can use this just for the distance or the displacement measurement, right? Okay, so sometimes it is most used in industrial company to have some of the robot or the automation procedures. Okay, and next one. It is also based on some the force balance accelerometer. Okay, so you can see here, this is the core. So with the vibrating, then we can get the vibration of this mass, and then we can get the signal from this core, electrical core, to detect the vibration. So somehow this kind of the force balance accelerometer is the most used for the vibration detection. Okay, and this is the one way. If you put this way, so this is for the X, and if you put in this way, this is for the Y, right? And the other side, vertical to the plate, this is for the Z. So usually we may have this kind of the 3-axis accelerometer, okay, X, Y, and Z, also for the different direction. So this is mostly used for the vibrating of the bridge, okay, or even to the earthquake. Depends on the sensitivity at all. Okay. And the next, I would like to show you, this is also the concept of the electromagnetic wave. So this is what we call the eddy current. Maybe, I think most of you already learned of this before in the senior or the junior high school. Okay, so this is the concept of the eddy current. If I have a core with the existing magnetic field, EM field. So if I close to the plate, then we may have a response from the plate. Okay, so based on that, we can use this for the distance measurement. Okay, so I think this is a very simple idea so far, using based on the principle of the eddy current. Okay, so compare compared to the previous one, I mean the LVDT, like this one. You already showed this is the LVDT, but I need a core, a steel rod, to detect, to touch the plate, right? For the displacement measurement. But however, if you use the eddy current, I mean that this is the non-contact measurement principle at all. Okay, so compared to the LVDT, this is the advantage using eddy current so far. And the next, I would like to show you another also electromagnetic field change based on the Hall effect. Okay, so it still have it still have has its own EM field, and also this is I mean that this is a similar concept compared to the eddy current. I think this is a similar idea. Okay, so with that, if I have the change, I mean the external change of the EM field, so I can check out the voltage change. So somehow, what kind of the situation will change the EM field? For this kind, if you have the encoder, like this one, we have so many tools. So when I have this for the spin, rotate, and each time I may have the signal like this one, right? For this, and for the long distance, maybe I get another signal response. Okay, so this is the Hall effect so far. So based on the Hall effect, if I can use this for the variable reluctance transducer. I think this is the simple idea at all. This is the Hall effect signal here. Okay, and this is the what we call the eddy current. Okay, I think the same. Okay, so based on the Hall effect, I can get the signal like this one. This is just like the vibrating wire sensor. I just mentioned that. Okay, so with this, this is the I think a video for you to show what is the Hall effect with the wheel, and this wheel may have a different speed, what we call RPM, the rotation or the speed per minute, maybe or per second per hour. Okay, so and let me show you the video. Oops.
Look at how a wheel speed sensor works and its basic components. Here's the tooth ring. This is a steel tooth ring with 48 teeth on it. Here's a variable reluctance sensor.
So this is the Hall effect
change in
sensor.
inductance
Okay.
as the tooth ring rotates. Okay, here's a breakdown of all the pieces that make up a wheel speed sensor. First, we have the tooth ring. Here we have a steel tooth ring. It's mounted on an aluminum mounting bracket. The aluminum bracket was custom machined by Gary Mathis at CHIH-CHUNG. Then the variable reluctance sensor. It's a coil wrapped around a magnet. You can see here the magnetism between the steel tooth ring and the reluctance sensor. The two ends of the coil are shown here. They're prongs. Typically, they're attached with a connector.
And let me
which is then
to
hooked into the computer with the oscilloscope.
So you can.
And here you can see on the oscilloscope
not so easy to
frequency generated by the
find.
variable reluctance sensor.
In the right side, there's a wheel. change
Let's zoom in.
speed.
See the signal, and it's giving a frequency of 258
So you can find the
hertz.
signal with a step.
Okay, so we have a
So let me
frequency
go
in
back.
38 hertz. So we have our steel tooth ring and the reluctance on here. The prongs, motor, the sensor. Then, when we get the motor, and here you can see on the oscilloscope the frequency generated by the variable reluctance sensor.
Okay, so I'm not sure, it is not so hard to find, but you can find this is the signal with the step here. So we can count, also using the same idea of the vibrating wire sensor to count how many steps, maybe in 1 minute. Okay, so this is the frequency. So I think it is very easy to use. So someone can help me which application can be used based on this, I mean, a variable reluctance transducer. Rotation speed. Okay, so I think this is a very direct idea. So if you have to drive to the school or to the market, so how can you know that the speed? So basically, it is using the rotation speed of your wheel, and use this the variable reluctance transducer. Okay, and the other one, can someone provide the maybe another one application? No? Maybe I can give you some hint. If this is what we call an encoder, and maybe I put the weight here, and this is the another weight. So this weight may be controlled by the ground or some that movable surface. So maybe we can use this also for the distance or the spacing measurement. Okay, so if I can detect the displacement here, means that the wheel may change. But however, this is a very low frequency, but I can still find the change of this variable based on the variable reluctance. Okay. So far, I think it can be used for the wheel speed and also the distance measurement at all. Okay, and the next, I would like to show you the electrolytic level. This is a level measurement. Okay, so this is the very basic idea. And inside we have the liquid. And we measure the difference voltage between these two terminals. Okay, so if I have the unbalanced situation, we can detect the degree of your sensor. So this is the original type. And the next, we use the MEMS. Maybe next I will talk about what is the MEMS. It is the micro electromechanical sensor system. Means that we're using a semiconductor to minimize the sensor based on maybe the strain gauge or this kind of the electrolytic level. So I think everyone in your cell phone, you do have this kind of the sensor. So if you right now I have maybe, how can I find where is the okay, I don't know because I have only the iPhone type. So if you open a compass, there's a circle if you have a different angle, it will show you the different angle, right? And you need to notice maybe this is the two axes, X and Y. So maybe inside of your iPhone or the Android system, you have two sensors. Take care the different position. I mean the different axes. Okay. And of course, you have a compass sensor inside. So right now, this is the MEMS technology. So help us to minimize the sensor size into your cell phone. Okay. So far, any questions? I think this is a very simple introduction at all for the most kind of the electrical sensors. And the next, I would like to show you a very unique sensor, what we call a piezoelectricity. Okay. So for the previous sensor, all of this sensor need input of the power supply, right? I need a power supply or the the input of the voltage. Then I can get the output of the voltage at all. So for the most previous sensor, I need input, and then I get a output, and then this output is based on the variation of your displacement, your pressure. Okay. However, for this kind of the piezoelectricity, it is very, very unique. How can I say that? Because if you use the piezoelectricity, if this piezo film, have the strength, then it will generate the voltage itself. You don't need the input of the voltage at all. Okay, so this is the concept of the piezoelectricity. So if you have a strand, maybe the small one or extension one, this is a compression or is a extension. So if you have the strand, they will generate. It will generate the voltage. Okay, so I think for this one, this is very, very, very unique one. And then here I show you a video. So this is a piezoelectrical film. Okay, so you can generate the voltage itself. Okay, so I think, and by the way, how can I use this kind of maybe the piezoelectricity for the monitoring? Can you image some application? If you have this kind of the piezo film, what can you use for the field monitoring?
You put it on a structure, and if it moves, you then get a signal that it moves.
Yes. Okay. Any else? In the last time, who present the bridge failed case? Okay, you, right? I think in Taiwan, mostly we have the scour. Do you know what is the scour? Scour problem. It's mean that maybe I'll show you. Okay. Scour problem. Okay, let me show you here. Okay, this is the bridge. So this is the deck, and this is the riverbed, right? So maybe I have a bridge, and here with the foundation. Okay, but in the Taiwan, we have a very severe problem is that scour, because this is the water level, and with the very high speed of the water, then we may have a very big problem of the scour. Means that the material will be flushed out during maybe the typhoon event. So mostly in Taiwan, we have several the bridge failure problem, and most of this is because of the scour. So right now, the Professor Wang, 有没有人？我们这边是结构组的。Is there anyone advised by the Professor Wang? Okay, the Professor Wang proposed a very good idea using a piece of film, because if I enlarge this one, this is the pier or the foundation. Okay, so if I can have some electrical film on the surface, okay, and if this sensor need to install earlierly, and if I have the cover, means that there's no signal at all. If I have a very good cover, because the piece of film is fixed, right? Buried on beneath the sand. But however, if I have a scour, means that the surface change to this one. So this is the under the water. So this piece of film will be vibrated with the flow. So I may get a signal here with the time, but under the riverbed, this is no signal at all. So based on this, I can tell the interface. I mean, due to the scour during the typhoon event. Okay. You mean this piece of electrical field? Very, very cheap. But I would like to say it is just the concept. You need to think about how can I install the piece of film in the surface of this pier or the foundation, and without the damage, right? If you already damage the film, means that there's no function at all. But I would like to say all the transducer and all the sensor are good in a laboratory, okay? But however, if you try to put this sensor in the field, you need to think about it. How can I fix? How can I protect? And how can I get the footage or the measurement output from these sensors? So I think there will be more practical issue for install and the sensor and the monitoring. Okay. Besides, I think this is another application of the piezoelectricity with some the vibrating sensor. Okay. Okay. Now I would like to show you man's concept. It is the micro electro mechanical system. I mean that. Let's go back to the strain gauge. Okay. The strain gauge. I think in the last time I just show you a very small one attached on a straw. But however, maybe this is just half fingers the size. But if I try to minimize the size of the strain gauge. How can we do that? So this time we need to use the technology, what we call the MEMS, micro electromechanical systems. So just I say that we use a semiconductor technology to minimize the strain gauge, I mean the shape of the strain gauge to the very, very small one. So that's why we can put the sensor, oops. There's a problem with my keyboard again. Okay, let us sorry for that. Sometimes. Okay. Okay, we are just talking about the MEMS sensors. So it's just used a semiconductor. You know that in the Taiwan, the semiconductor technology is very, very powerful in the world. So we use this technology to develop a very small one sensor based on the strain gauge. So of course, we can use this technology to minimize the strain gauge and also into the different kind of the application we just mentioned at all. Okay. So this is the MEMS, and right now all the sensor inside your cell phone is based on the MEMS sensors. Okay. And the next, we just finished the electrical instrument so far. So if you have any problem, I think I give you already some of the introduction of this sensor. If you try to have much detail, you can Google that. And the next, I would like to show you another principle using acoustic, like the supersonic. This is what we use mostly for the level meter, for the water measurement or the liquid measurement. Okay, so this is the sensor. Acoustic wave, and this is the non-contact technology, because we just using a wave here, and we may have a reflection of the wave. Okay, so this is not only used for the liquid, and maybe used for the powder or some food, the rice or any kind of the agriculture. Okay, so this is a very simple idea for the level measurement, and based on that, in the ocean or the hydrological measurement, this is another very famous instrument, what we call oops, 又来了。Sorry. Okay, this is what we call ADCP. ADCP, acoustic Doppler current profile. Okay, so what is that? As has anyone heard here know that the Doppler principle? Okay. So this is, I think, this is the principle of the Doppler. If I have the particle movement forward, I may have a very lower response of the acoustic wave. But if I have a approaching particle, so that I may have a very high frequency of the response. Okay, so that's why the acoustic profile can be used for the what to check the water flow. So for this kind of the sensor, they have a different direction of the acoustic beam to measure the water velocity in a different direction. So somehow this kind of the sensor may be fixed at the bottom of the river or the ocean, and this is the beam. Okay, so you can have a different direction to measure the water velocity. So based on this, we can get, oops, sorry. Actually, we can get the profile of the water velocity, maybe 2D or the 3D if you have several ADCP at all. And otherwise, and additionally, we can also get the concentration. Why? Because in the previous, just I said, oh, sorry. We use the particle inside the liquid or in the water to detect the velocity. This is the principle to measure the water velocity or the flow velocity at all. At the same time, because we just measure the frequency of the response, at the same time, if we can measure the echo intensity, I mean the amplitude of the response, so I can also measure how much of the concentration, I mean the particle concentration inside of this water. So it means that we can measure the suspended sediment concentration. What is the suspended sediment concentration? It means that this is the tank of the water and there's a lot of particle inside. And this is the suspended, okay, with the flow. So we can measure the concentration meanwhile because we can measure the echo intensity, I mean the amplitude of the refraction. So we can use that to mapping a concentration map. So in the red area means that there's a lot of suspended particle, sediment particle. Okay, and this is very important, especially for the hydrological field. What is that? You need to know the water level. You need to know the water flow velocity. And the next one, you need to know that the concentration of the sediment. So based on this information, you can decide maybe the infrastructure, like the bridge, like the dam, okay, like the river bank, based on this information. Okay, so this is the typical result from one master thesis in the 2011. Okay, and I also want to mention that not only the refraction, we can get for the industrial field. They also use the transmission attenuation at all. So for this kind of the sensor, okay, this is the output, and this is the receiver. Okay, so the receiver can estimate how much of the attenuation due to the what? Also the particle. Okay, so this kind of the transmission attenuation mostly used for the also the sediment concentration, and for the industrial field we used to measure the metal concentration at all. Okay, so this is a very simple idea. But however, I would like to say this kind of the transmission based on the acoustic, because the wavelength is limited. I mean, the wavelength is much larger compared to the particle. Okay, so if I have a different particle size, maybe I may get a different response of the attenuation. So that's why we need a calibration again. Okay, so I need to know how much attenuation it is, and what is the actually the concentration at all. If you have a different particle size, maybe you may have this, because I have a different regression line at all. So this is maybe some limitation using the acoustic attenuation to measure the particle concentration. So you need to know that this is a limitation. Okay, compared to the acoustic one, next I would like to introduce the optical instrument. So this is the very popular one, total station. Anyone used that before? No. I think in a Taiwan University, we have a course to let the student to operate a total station to measure maybe the target elevation and the angle. Okay, so this picture I just cited from the BESS 2012 in maybe in Netherlands. Have you been there, Netherlands? No, for the smoke? No. Okay, so I think in Amsterdam, okay, I also found this total station in a different location. They mount the total station here, just maybe in the second or the third floor, and they try to measure the displacement of this target. Because of what? Because in that time, there is subway construction. So they try to make sure that if there's any problem, I mean the house due to the instability due to the construction. So this total station can be automatic, measure the target. Okay, by the program. So I think it is a very useful. But however, I would like to say sometimes it is limited with the weather. Okay, and also the resolution depends on your equipment. Okay. And next, I would like to show you application using optical sensors. This is what we call a turbidity meter. Okay, and what is the turbidity meter? Is try to find the how much clean of the water, drinking water. Okay, so for the turbidity meters, they have several principle of the measurement. For the mostly, it is using the backscatter or the 90-degree detector or the transmission. Depends on the transmitter and the location of the receiver. Okay, so here I send a light source from the left side, and then I can get the backscatter because this is the large degree of the refraction. Okay, this is what we call a backscatter. If I put the receiver in the 90 degrees, so this is the what we call the nephelometric. Hard to say. Okay, and this is the 90 degrees sensors. And if I put the receiver in the other side, the opposite side, this is what we call the transmittance detector. Okay, so based on this different kind of the angle, we can get the different the value of the turbidity. So the next time, if you have to buy, or if you need to proceed a project to measure the water turbidity, and you need to ask the commercial company, say that what kind of the sensor we need to use. Okay, so for the mostly the backscatter, this one is used for the backscatter in the field. So I can put a sensor inside of the water, and with the reader to show the observation. And for this one, this is the transmission one. It's most used in the laboratory. So maybe for the mostly, I put the water with a tube, and this tube will put inside of this equipment, and using the light source to detect the response. So if there's too many particles, the response may be changed. So I can tell the clean or not of this water. So this is what we call the turbidity. And of course, this is also 90 degrees in the field. So what is the turbidity measurement? This is the picture maybe in the 2015 in the Taipei. Wulai. Have you been there? Wulai for the hot spring? No? No? So next time you can take them out. 乌来有没有人去过？你们有去过吗？乌来。So this is the picture during the typhoon event in the 2015. So in that, this is the, I mean, this is the very important source, water resource for the Taipei County, Taipei area. But in the 2015, you can find the water is too dirty because of the sediment from the upstream. Okay, so in this time, I think the water supply may be suspended more than 1 day or 2 days. Okay, I forgot that. But you can imagine that for the whole Taipei area, millions of the people without the water supply, it is a very important issue, and this is the political issue at all. So So after the 2015, they tried to develop some strategy and some automatic measurement for the water turbidity, especially in the typhoon event. Okay. So right now, the water supply will be a very important issue based on the water turbidity. Okay. And the next, I would like to show you another application using the optical instrument. It is what we call the dust, PM10 or PM2.5. Okay, so here, this is the idea of the sensor or the transducer. So you can image that the particle is much smaller than of your compared to your hair. So very small particle, and we use the lens and the source of the LED, and then we can get the reflection. Maybe, oops. Again. I need to replace my keyboard. 伤脑筋. So maybe we can have a short break, okay? And is there someone need to present your first homework? How many? 1 and 2? Only 1? And Yan Kai, not represent. 你报过了 okay. So how many? Only 1? Okay. So maybe later you can show your presentation, okay? So let us have maybe 5-minute break. Hey, 我可能要找一下，等我一下哦。